Recording in.
Okay, so welcome to 150. This is lecture 18. So the new content today is going to be discussing how we're going to do differentiation of functions of several variables. And so we touched about this already a little bit. We've already seen one application of this when we were discussing regression or the method of least squares. Before we do that, though, I want to just go over a problem that's related to things from the exam. It's a little bit harder, and just walk you through how do you write something up very carefully, cleanly. There's a lot of places where it's clear that you know what you're doing, and I have done math long enough that I know what you're doing, but what you've written down is not actually right. You have dropped the word limit in places, or you have the function in the first derivative equaling the same thing. You've got to be very careful in how you write things up so that somebody can follow and see what you're doing. And again, if you have any questions, INTs are always happy to meet with you and discuss, how should you write these things up clearly? That's the skill that's going to be extremely valuable when you leave this class and move on in the world. How do you write things up in such a way that you can communicate with someone in terms of what's going on? You might say, but come on, it's clear that I know what's going on. Yes, but on the very next line, you dropped a minus sign, or on the very next line, you did something wrong. And so how do I know that you were doing it correctly here? So on exams, you have to put in the details. All right, so let's do a slightly more challenging problem than I would have given you on the exam. So let's calculate the limit as x goes to infinity of, do you want it to converge or diverge? Diverge, all right, there we go. Let's start off the day with a diverging. 2 to the n plus 3 to the n over n squared plus n cubed. Okay. So we want to study whether or not this converges or diverges. So there's a couple of things we can do. The first one is, do the terms go to 0? No. Don't have to worry about ratio tests. Don't have to worry about root tests. Don't have to worry about comparison. The terms don't go to 0. Done. So as an does not go to 0, it diverges. If you want, by all means, you can use a more elaborate test to show that it diverges, but there's no need. Always try to do the easiest thing first. All right. Let's modify it and let's flip it. Now let's do it as n squared plus n cubed over 2 to the n plus 3 to the n. Now the terms tend to 0, so it has a chance of converging. So as terms approach 0, has a chance to converge. So now we have to think, what do we, yes?
So when you were eyeballing some of these diverges, is this based off of the assumption that exponentials grow faster?
Yes, and that's something that we should know. Your exponentials grow faster than polynomials, and we can quickly prove that using L'Hopital, and I'll do that after this. When we're looking at this and we're trying to show that it converges, if I wanted to use the ratio test or the root test, it's not going to be pleasant because I have these sums. So there's a couple of things you could do. I could try to pull out some items. I could write n squared plus n cubed over 2 to the n plus 3 to the n. You pull out the highest power, n cubed, 1 plus 1 over n, pull out a 3 to the n, 1 plus 2/3 to the n. And if I just pull out the main thing, okay, it kind of looks like n cubed over 3 to the n. So if I can figure out what's going on with n cubed over 3 to the n, I should be able to figure out what's going on here. All right, let's do it a little bit more rigorously. I want an upper bound. So find a bn such that 0 is less than or equal to n squared plus n cubed over 2 to the n plus 3 to the n is less than or equal to bn, and the sum of bn is less than infinity. So if we can do that, then we know it's going to converge. So I'm just looking at a slightly harder problem I gave you. The addition makes it a little bit painful to do the ratio test or the root test. So I want something a little bit larger than n squared plus n cubed over 2 to the n plus 3 to the n, but I still want it to converge. Can somebody give me something close to the numerator that will be much easier to work with rather than n squared plus n cubed, something a little bit bigger? No, but close. No, well, n squared is less. You made it so n cubed is not larger than n squared plus n cubed. You're close though. So rather than replacing with n cubed, I could replace it with, I'm sorry? You could do n to the fourth, but then you would have to show n squared plus n cubed is less than n to the fourth. Well, again, you would still have to show that. If I have a series that converges, if I multiply by 2, does it still converge? If I multiply by 5, does it still converge? 2n cubed, right? That's why you were so close. So note, n squared plus n cubed is less than equal to 2n cubed. And if you're going back to what we had a moment ago, I'm pulling out the n cubed, I have 1 plus 1 over n. Well, once n is at least 1, okay, that happens really fast, 1 plus 1 over n is going to be 2. And then as long as n is greater than 1, 1 plus 1 over n is going to be less than 2. The other way of looking at it is, well, n squared is going to be less than n cubed whenever n is a positive integer. So this is going to be a fine approximation. So if I replace the numerator with 2n cubed, I just make it larger. If it converged before, this could push it to diverging. If I replaced n cubed with 3 to the n, that could cause problems. But if I show the new thing converges, then the old thing had to converge as well. So what about the denominator? Do I want to make the denominator larger or smaller if I'm trying to do convergence? Smaller. So can you give me something, 2 to the n plus 3 to the n is greater than or equal to what? Yes. You could, but it's going to make things painful. Let's make things as simple as possible. I want to do easy algebra. So if I make the denominator smaller and it converges, then the original thing converged. What would be a good choice for a smaller denominator? So I have n squared, I'm sorry, I have 2 to the n plus 3 to the n. What would be a good idea for a smaller denominator? Nope. Just 2 to the n. Right? I'm trying to make it smaller. So just drop the 3 to the n. And this comes back, from looking at what we did before. The bottom was 3 to the n plus 1 times 1 plus 2/3 to the n. If I wanted to see the true size of the denominator is going to be of size 3 to the n. Absolutely. And if I'm dividing by 3 to the n, that's going to make my fraction much smaller than just dividing by 2 to the n. So I could also do, or I could do 2 to the n plus 3 to the n is greater than or equal to 3 to the n. I could do that. That's also going to work. Which do you think is safer to do, 2 to the n or 3 to the n? Well, but the danger is maybe the original thing converges, but because of my approximation, what I approximate with diverges. So which do you think is going to be closest to the true size of the denominator? 3 to the n. So I would say 3 to the n is a little bit better because you're not throwing away as much stuff. Now, it turns out for this problem, either 2 to the n or 3 to the n would work. So what we notice, the above shows, n squared plus n cubed over 2 to the n plus 3 to the n is less than or equal to 2n cubed over 3 to the n. So by the comparison test, if the sum of 2n cubed over 3 to the n converges, so too does the original series. Okay. So we've now reduced it to just studying the problem 2n cubed over 3 to the n. I just wanted to use the comparison test first to make the algebra easier. Do you want to use the root test? Do you want to use the ratio test? Any thoughts? I'm a fan of the ratio test as well, right? I would much rather try to use something that's easier, taking ratios of numbers versus taking roots. Let's try the root test. So try root test. Yes? Oh, sorry, not root test. I'm sorry, I want ratio test. Sorry. No. I mean, if we do the root test, we'll also get a convergence.
No, so if we did the preliminary one, which is like just plugging in.
Oh, just do the terms tend to 0.
Yeah.
Yes.
That's the assumption.
Right. I mean, you don't have to check to see if the terms tend to 0, but since that's usually the easiest thing to do, do that before you go ahead and do everything else. We have Bn was going to be 2 times, was it 3 to the n? What we had? Oh no, 2 times n cubed over 3 to the n. Okay, 2 times n cubed over 3 to the n. So rho is the limit as n goes to infinity of bn plus 1 over bn absolute value. And I have to keep writing limit every single time. If I just write now 2 times n plus 1 cubed over 3 to the n plus 1 over 2 times n cubed over 3 to the n, that's not a true statement. I'm calculating the limit as n goes to infinity of this ratio. If I drop the word limit, I now have a fixed expression for a fixed value of n. That's wrong. That's not the same as what I have. I have to make sure I keep writing take the limit as n goes to infinity. Okay, well, a lot of things cancel. The 2 cancels here. 3 to the n over 3 to the n plus 1, that's going to cancel and just give me a 3. And so I'm going to get the limit as n goes to infinity. I'll have an n plus 1 cubed over n cubed. And then I have a 3n plus 1 over 3. So I'm going to have a 1 over 3 down below. And so this is just going to be 1/3 the limit as n goes to infinity of n plus 1 over n cubed, or if you want 1/3 the limit as n goes to infinity of n plus 1 over n all cubed. Either of those is fine. What's the limit as n goes to infinity of n plus 1 over n? 1. 999 over 1,000. 1,000,001 over 1,000,002. It's getting closer and closer and closer to a ratio of 1. So this is just going to equal 1/3. And then just write, as rho is less than 1, by ratio test converges. And this is a good, clean way of writing what we're doing. Okay, as an aside, there was a question about polynomials versus exponentials. So this is a great application of L'Hopital's rule. So let's compare, x to the m versus b to the n. Or more generally, x to the r versus b to the a, where, say, a and r are greater than 0. So the claim is x to the r over, this should not be, this should be just x over here, sorry. The claim is x to the r over b to the x goes to 0 as x goes to infinity for b greater than 1. Why do I have to take b greater than 1? Well, if b equals 1, b to the x is just always 1. If b is less than 1, as I take higher and higher values of x, I'm going to get a smaller and smaller number. So we'll take some base greater than. Okay. I'll do e to the x to make things simple, and I'll just discuss about the general. For example, x to the r versus e to the x. Now, if we want to use L'Hopital's rule, if r is an integer, then eventually it will stop. I only have to do so many derivatives before it's going to stop. But if it's a fraction, well, I might have to keep doing more and more and more. I would have to do infinitely many. But eventually I will get a numerator that will be fine. So let's do the following. Without loss of generality, let m be the smallest integer greater than or equal to r. If we can show x to the m over e to the x goes to 0, so too does x to the r over e to the x, as x to the m is greater than or equal to x to the r. So I'm just saying, without loss of generality, I can make my life a little bit easier and say I might as well assume the power of x is an integer. Because if it's not, just take the next integer, greater than or equal to r, do the analysis there. And then since x to the r is smaller than that, if x to the m over e to the x goes to 0, then this would go to 0. And so now we would look at the limit as x goes to infinity of x to the m over e to the x. This is 0 over 0. I'm sorry, this is infinity over infinity. So we use L'Hopital. And we get m x to the m minus 1 over e to the x. Is that correct?
Yes.
I have to keep remembering to write the word limit. If I don't write the word limit, it's wrong. I still have infinity over infinity unless m equals 1. So I would take the derivative again. I would get, L'Hopital limit as x goes to infinity of m minus 1 x to the m minus 2 over e to the x. And then we just keep doing this. And eventually we get the limit as x goes to infinity of m factorial over e to the x, which is 0. And this would prove that the polynomial is growing slower than the exponential. If instead have b to the x, this is the same as e to the x natural log of b. Once you hit college, we stop writing ln for natural log. We normally just write log. And so if I have this, then we would note that the derivative of b would just be e to the x log b times the derivative of x log b. What's the derivative of x times the log of b? So what's the derivative of x? What's the derivative of 15x? 73x. X natural log of b. I'm sorry? Just log b. The log of b is a constant. So this would just be b to the x again times the natural log of b. So the only change is that every time we take the derivative of the denominator, we get an extra factor of the natural log of b. So the same type of analysis would work as long as the base is greater than 1. And we need the base to be greater than 1 so that we get infinity over infinity. So again, this is how you would attack problems like this. You're going very carefully. If we wanted to use the ratio test, we saw it wasn't so bad. If we want to use the root test, we would have to take the nth root of 3 to the n. Okay, that's not so bad. The nth root of 3 to the n is just 3. Then we would need the nth root of n cubed. Okay, well, that's take the nth root of n and then cube that. So you would have to show that the nth root of n is 1. We've done that before. I'll just do that again as it's a fun problem. So as an aside, the nth root of 1 over n, if we take the limit as n goes to infinity, is just 1. And if you want to build up some intuition, you could take maybe n is huge powers of 2 and just play with this a little bit. So what I love is the following. I love taking logs. Study the log of n to the 1 over n. that's going to be the log. It's going to be 1 over n, the log of n, which is the log of n over n. So if I can understand what the log of n over n is going to, if I exponentiate, I then understand what n to the 1 over n is going to. And so if we take the limit as n goes to infinity of the log of n over n, how would we handle that? So as n goes to infinity, what does the log of n go to? Infinity. And n goes to infinity. So we have infinity of infinity. What should we use? L'Hopital. So you can L'Hopital it. And this would be the same as the limit as n goes to infinity. The derivative of the natural log of n is just 1 over n. The derivative of n is just 1. So that limit is 0. So as the log of n over n goes to 0, the exponential of the log of n over n, which is just n to the 1 over n, goes to 1. A more advanced way of doing this is I could let n equal e to the x. So as n goes to infinity, x goes to infinity. Thus the limit as n goes to infinity of the log of n over n would be the same as the limit as x goes to infinity of the log of e to the x over e to the x, which is the limit as n goes to infinity of x over e to the x. But that's 0. We just did it. This is a more advanced way of doing the problem. It's reducing it to something we've already done. We know, we just showed that the limit of x over e to the x, or x squared over e to the x, or x cubed over e to the x, x to any power grows slower than e to the x. So when I have the log of n over n, if I just change variables, you give me an n, I'll give you an x that corresponds. As n goes to infinity, x is going to infinity. And so when I do this, I can just quickly reduce this to a problem I've already done. Right. So this is just a good way to review, some of the stuff we've been doing up till now, how to write things up very clearly, things you've got to be very careful about not dropping. It takes a lot of time, and I know, frequently in your mind, it's clear what you're doing. As you go further, things get less and less clear, the arguments become more and more involved, and the more things you write down, the more careful you are, the less likely you are to make a mistake. A lot of this is getting into good habits. I know a lot of times in school, people are frustrated. Why do I have to put in so many details on something that's so obvious? Well, the reason is because as you go further, it stops becoming obvious. The quantities become more involved. It's very easy to just drop a term or to misapply something or to not make sure all the conditions are met. So it's a good habit to just get into writing things up. This is why I give you detailed solution keys and say, here are some common mistakes. Really look at those and get a sense of how to write things up. Okay, so the plan for today was we reviewed writing up problems. So we talked in the past about the derivative in one dimension. We talked a little bit about partial derivatives and that there were 3 ways of writing the derivative in one dimension. We talked about f of x plus h minus f of x over h. We also talked about writing it as f of a minus f of x over a minus x, where other way around. So f of x minus f of a over x minus a, with x going to a. And if you really just let x be a plus h, it's the same as what we just did. And then the other way of writing it was to talk about the tangent line. And so this was another way to discuss the derivative. So the derivative, it could be f prime of a is the limit as h goes to 0, f of a plus h minus f of a over h. It could be the limit as x goes to a, f of x minus f of a over x minus a. And it could also be the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a. And that limit equaling 0. that's equivalent to what we're doing. Because if you look at what goes on, the first part over here, this is looking like f prime of a. So this looks like f prime of a. And this part over here looks like f prime of a, x minus a over x minus a, which is just f prime of a. So saying that this difference equals 0 is equivalent to saying that f prime of a is exactly what we've been working with all along. You can view this as look at f of x, subtract the tangent line approximation, show it is so good, you still go to 0 when divide by x minus a. Imagine you're driving a car at 60 miles per hour. And I know after 1 hour, you're 100 miles from home. Can somebody give me a good, quick approximation of where you are 1 second later? I'm sorry? 100 miles, right? If I'm measuring things in miles, and I'm talking about where am I 1 second later, 100 miles is a very good approximation. What if I told you I was driving at 20 miles an hour? What would you say for your approximation? 100 miles. What if I told you I was speeding and at 85 miles an hour? Still 100 miles. They're all going to be very close. If you look at the difference between where you are and your initial approximation, it's negligible. So if you say, hey, look at how close they are. Well, yeah, they're close because really not much time has elapsed for things to really happen. I want to measure things in a natural scale. And so what I want to do is I want to measure things not just by how close they are, but how close they are relative to how much I've moved. And so if I'm looking at 1 second, that's a very small amount of time. And so if the distance between f of x and f of a is small, okay, it's small, great, but so is the amount of time. And if I look at their ratio, what's going on? And so now, if I just looked at f of x minus 100 and divided that by 1 second, that's now going to be sizable. The whole point here is that when I subtract off the tangent line approximation, the tangent line does such a great job that even when I measure the error relative to that small amount of elapsed time, it's really accurate. And this is why you often see pictures like this, where here is my function, and then here is my approximation to the function at a point, and locally I really can't see the difference. And so if the function is nice, the error is going to be of size x minus a squared. So if x minus a is of size 1/60th of a minute, or 1/3600th of an hour, my error might be on the size of that squared. Very, very small. And so as x gets closer and closer and closer to a, the error is going to get smaller, and it's going to get smaller really fast. It's not going to be essentially like a fixed error. The difference is going to be getting so small that even when I divide by x minus a, it's going to be accurate. So the question is, how do we generalize this to functions of several variables? So we talked about, well, we could introduce partial derivatives. So df dx means take the derivative with respect to x, all other variables fixed. So for example, if I give you f of x, y, z is, x cubed plus, the sine of y to the z, sine of y, tangent of z plus y squared. Okay, I think I have enough parentheses. I have no desire to take the derivative with respect to y. I have no desire to take the derivative with respect to z. But the derivative with respect to x, that's not a problem. I'm keeping y and z fixed. That nightmare, the sign of good Lord. It's just a number. It's a fixed number that has no x dependence. So here, we would just get df dx would just be 3x squared. Now, if I wanted to calculate df dy, could I do it? Of course. What would be the derivative of x cubed with respect to y? 0. And then I would have to take the derivative of sine of, okay? And so I would have to start using the chain rule. So I would get, df dy, okay, so the derivative of sine is going to be cosine. So I would have, the cosine, let's see if I can do this quickly. Oh, good, it worked. So I'd have the cosine of that quantity, right? Then I would have to multiply by the derivative of that quantity, right? So I'll write it as d by dy of this quantity. Oops. Right? And then I would just keep going. I cannot stump you in a differentiation. I can make you hate me. I can make your life unpleasant. That's easy to do. But I can't stump you. You just keep hammering away with the rules. And I treat z as a constant. So what would I use next here? I have y to the z times sine of y times tangent of z plus y squared. What would I use next? Product rule. So you're in trouble unless you remember the triple product rule. And if you don't remember the triple product rule, then you would have to use the product rule twice and group things together. So maybe I would group y to the z sine y together as one term. But, all right, develop a triple product rule. That's next on the to-do list. And you just keep hammering away. So these are the partial derivatives. This is what's happening if I move in just one direction. In one variable calculus, there's really only one way to move. I move right, I move left. I'm just moving along a line. In several variables, I have many different ways to travel. And so the question is, if I know the partial derivatives, is that enough to understand what's going on? Well, this is why we spend all this time learning equations of lines, equations of planes. The goal is, rather than trying to say, hey, a function is differentiable in one variable if when I subtract the tangent plane and divide by the amount I move, that tends to 0. Well, the natural suggestion then for several variables is to subtract the tangent plane or the tangent hyperplane. So in 2 dimensions, f of x, y is differentiable at the point AB if the limit as xy goes to AB. Now we'll do f of xy minus f of AB. And now we have to subtract off the tangent hyperplane. And that's going to be the partial of f with respect to x at the point AB times how much I move in that direction, minus the partial of f with respect to y at the point AB times how much I move in that direction, divide by the distance from xy to AB. And I want this to equal 0. Okay. And so what we're doing is we take where we start and we subtract off the tangent hyperplane. Another way of looking at it is, imagine a simple path where y is always equal to b. Then we should be subtracting off the tangent line. If y equals b, we don't have the second term, and we just have the tangent line in the x direction. Similarly, if y equals b always, we're subtracting the tangent line in the x direction. If x equals a always, similar in the y direction. Okay, so this is a very natural formula for the tangent hyperplane. It reduces to what it should. If I don't have a y variable, I should be just subtracting off the tangent line. That's what I'm doing. If I don't have an x variable, I should be subtracting off the tangent line in the y direction. That's what I have. And this is just saying this is what the combination is. So a function is differentiable if when I subtract like this, it tends to 0, even when I divide by the length of the distance I've moved. If you want, I could put an absolute value in the numerator. Doesn't really matter because the numerator is just a number. So if it's going to 0, I don't care if it's going to 0 by hip hopping, plus and minus of 0. However, x, y, and a, b, these are vectors. These are points. And so I can't just do the pair x, y minus the pair a, b. I can't divide a number by a vector. So what I'm doing is I'm dividing by the amount I've moved. And that's going to be something that's reasonable. Now, if I had 3, yes.
What do you mean by similar to the y direction?
Oh, just it's similar. If I'll get a tangent line in the y direction. So what you always want to do is you always want to try to reduce whatever new thing you're looking at to something you already know. And so if I only had one variable, I should be subtracting off the tangent line, and this tangent plane is collapsing to a tangent line if I always take y to be b, or if I always take x to be a. If I had 3 variables, x, y, and z, what do you think I would have to include? I'm sorry? Yeah, so we would have z equals c, and we would have another term. What would be the new term if we had a new variable z? Well, we would have c as the new component, but we subtracted off df dx at the point, now that would be at the point abc times x minus a. We would have a df dy at the point abc y minus b, and what would be the next term we would have to have? So if we now had a new variable, df dz and abc. What if we had 4 variables? Then you often do w, x, y, z, and then does w come before x? Do we put it after? If we have, this is getting to be a nightmare. Dr. Seuss has a wonderful book on Beyond Z, where we've run out of letters of the alphabet, so he starts creating additional letters of the alphabet to help. Even if you read that book, it's not going to be more than a finite addition. At some point, you start to run out of letters, and it starts to become painful. So we often change to subscripts, and we just look at things a little bit more formally. So in general, let's say we have f of x1 through xn is differentiable at the point a1 ... an if the limit as x1 ... xn goes to a1 ... an of f of x1 ... xn minus f of a1 ... an minus the gradient of f at the point a1 ... an times the vector, well, it's not times, dotted with, and here it's going to be x1 minus a1 ... xn minus an, and then divide the whole thing by x1 ... xn minus a1 ... an is 0. So I deliberately wanted to write it in a very bad way to show you that we need better notation. This is taking up way too much space to write. So let's rewrite this using better notation. Let's let x be the vector x1 through xn. Let's let A be the vector a1 dot 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 an. And now we would get the limit as x goes to a of f of x minus f of a minus grad f at a dotted with the vector x minus a over the length of x minus a, where grad f is df dx 1 dot 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 df dxn. So the gradient of f at the point A dotted with x minus a would just be df dx1 at a times x1 minus a1 plus dot 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 plus df dxn at a xn minus an. Okay. This is far more concise notation. The further you go, the more important it is to have concise notation. So that, your hand does not get, overworked from just writing everything. And eventually you start to be able to just look at this and see what's going on. And you can see formally, this looks a lot like the old definition, except I put arrows over the variables. So instead of saying f of x, I have f of x with an arrow over it. Okay, it's f at the vector x. Instead of subtracting off f of a, I'm subtracting off f of a with an arrow over it. Okay, it's essentially the same thing. Now instead of f prime of a, I'm writing gradient of f. So we sometimes write here grad f, which is the gradient. This is our vector of derivatives. Okay, it's just a nice compact way of writing what we were doing. And again, this was done deliberately. This is a mess. I've got something over here. I've got an arrow pointing that it's supposed to go right over here next to the dot product. The thing is too long. Look at the word limit. I've got such a big thing underneath it. All right, maybe I can move the limit over there a little bit so it's, but that's huge. It's a nightmare to be writing all of this. We want good, clean, compact notation. So if this limit equals 0, then the function is differentiable. So, oops. So we say f is differentiable if this limit equals 0. Is that 0 the number or 0 the vector? Well, let's look at the numerators. The numerator, a number or a vector? I'm sorry? Well, I have vectors in the numerator, but I have, for instance, the dot product of two vectors. I have the dot product of the gradient and the vector of x minus a. Is that a vector or a number? No, everything in the numerator is a number. What about the denominator? I have the length of the vector x minus a. Is that a vector or a number? It's a number. So this is 0 the number. Okay. This is the definition of what it means for a function to be differentiable. Yes.
Is that a sum one?
Oh, that's a comma. I can remove the comma though. This is not one of the situations where the Oxford comma can make a difference. There have been multi-million-dollar lawsuits where people have argued that depending on where you put the comma, you can interpret the sentence differently. Anybody know the most famous expression? Okay, I like that one. I was doing panda eats, shoots, and leaves. Is the panda eating shoots and leaves, or did the panda shoot and then leave? So depending on how you put commas, you can change how you pass things. This is why we have the Please excuse my dear aunt. Okay, it's either Sally or Sarah. I heard Sally when I was young. It's nice to know that it's still Sally after all these years, right? We put in parentheses just to make it clear. Well, okay, I really want to be clear which operation I'm doing before the other operation. So over here, this is our definition of what it means for a function to be differentiable. It means the tangent hyperplane is doing such a good job approximating. And then the question is, it turns out that there are functions which have partial derivatives that exist but are not differentiable. And what that means is if you approach it in different ways, you can get different answers. You can't have this in one dimension because you really can't approach in different ways. Well, I mean, the best you could do in one dimension, you should always have examples of non-differentiable functions. In one dimension, consider f of x equals the absolute value of x. This is not a hard function for me to plot, which is why I actually have a chance of doing it well. If I look at the limit as x goes to 0 from above, the plus means from the right. So I'm coming in this direction, I would get f of x minus 0 over x minus 0. This is the limit as x goes to 0 from above. So the absolute value of x is just x. I get x over x. This is 1. I could do the limit as x goes to 0 from below of f of x minus, I guess I should write f of 0 here. Minus f of 0 over x minus 0. But now, since x is negative, what's the absolute value of x? If x is negative, what's the absolute value of x? No. If x is negative, what's the absolute value of x? Negative x, right? What's the absolute value of negative 4? It's 4. 4 is negative negative x. So this would just be negative x over x, which is negative 1. And these are different. So not differentiable. So here's a good example of a non-differentiable function. I get a different limit as I approach from the left or the right. If I'm coming from here, I'm always getting a plus 1. If I'm coming over here, I'm always getting a minus 1. So I don't get the same limit as I approach the origin. In one dimension, this is really all I can do. I can only move left and right. But in several dimensions, I have so many different ways to move. We now have to start worrying about what if I get a different answer depending on the path I take. This would be terrible for a lot of things in life, right? That the way you get there matters. Well, but we have a lot of experience with this. If you're putting money in the bank, if you put in the money and then the bank calculates the interest, that's different than if the bank calculates the interest and then you put in the money. Order matters. If you've ever worked on a Rubik's Cube, the order in which you spin things matters. For many things in life, order matters. It's very nice when, at the end of the day, it doesn't really matter how you got there. How many people have ever played one of the intellectual challenges of our era, tic-tac-toe? All right. If I show you the game state of tic-tac-toe, does it matter how we got there? No. All that matters is this is the game state. It doesn't matter how we got there. Now, if you're playing chess, it actually does matter because chess is a draw if you have a threefold repetition of a configuration on the board. Chess is more advanced than tic-tac-toe, and that's the only reason it's popular. So if I just give you a tic-tac-toe board configuration, I don't really care. So the last thing for today is some notation. So df dx, we sometimes write that as f sub x, is the partial derivative of f with respect to x. What's df dy? It's similar with respect to y. What about f sub xy? is this the derivative with respect to x of the derivative with respect to y of f, or the derivative with respect to y of the derivative with respect to x of f? They might be different. I got to give you something to wonder about over break. But again, it can be either, so long as we all agree on notation and convention. We have to decide which do we mean. When we write x, do we view this as fx, y? If we do it like that, then that would imply that we would first take the derivative with respect to x and then take the derivative with respect to, that we're reading from inside out. You could also read it the other way. It's a convention. It doesn't matter so long as we all understand what we're talking about. It would be terrible if you did things differently than everyone else. And so we'll talk about this, later in the semester. And it turns out as long as the function f is nice, they're the same. So if these two partial derivatives are continuous, then they're equal. Oh, okay. So as long as I work with nice functions, it doesn't matter. If I don't work with nice functions, then I have to be careful. All right, I will send an email for details for spring break. Have a great spring break, and I will see you in 2 weeks.